Hello and welcome back. In this video, we're going to go through an example of finding orthogonal projection. So both the orthogonal projection and the scalar component of u in the direction of v. So the scalar projection as well. So we're going to find those. This first slide here is just reminding you of these formulas that we came up with in the previous video, that if I want the vector, the orthogonal projection of u onto v, remember this is the one that returns a vector that's in the direction of v, and whose magnitude is how much u goes along v. That was given by this formula, u dot v over v dot v times v. And then the scalar component of u in the direction of v, or the scalar projection of u onto v, is u dot v over magnitude v. All right, so let's actually work out an example here. Here I have u and v, and I want the projection of u onto v and the scalar component of u along v. Okay, so first I just want to think about the geometry of this, because that's going to tell me if the answer I come up with is, in the right ballpark, or if I made some mistake in my calculation. So I'm projecting u onto v. So another way to think of this projection is like I'm taking a light. So let's say I have like a light here, and I shine it, perpendicular to u, or sorry, perpendicular to v. What I'm going to get here, so I want this to be perpendicular to v, is I'm going to get a shadow. So maybe my light isn't exactly where I want it to be. I want it to be perpendicular to v. I shine my light perpendicular to v like this. And what that's going to do is it's going to cast a shadow of u onto the vector v. That's going to give me this projection. That's my orthogonal projection of u onto v, and then the magnitude of that is my scalar projection. So I know my vector is going to look something like this. It should be in the direction of v, and it should be, it looks, I don't know, about half as long as v, something like that. That's the ballpark I'm going for. And so now let's compute these quantities. So I'm going to compute the projection vector of u onto v. That was, remember that the projection of u onto v is, what was this again? U dot v over v, v dot v. And that is multiplied, scales the vector v. So let's go ahead and compute that first. So I'm going to stress this again. These calculations for finding, say, projection or scalar projection involve many smaller calculations. So I'm not going to do those over here. I'm going to do those separately. This is a good way to make sure to just kind of keep track of your calculations, so that if something goes wrong, if you get something that's not in the right ballpark, you can go back to all these smaller calculations and verify those, and then see how they combine. So u dot v, that's going to be what? 4 times 3 plus 1 times 4. So that's 12 plus 4, that's 16 is u dot v. And then v dot v is, let's see, what's the magnitude of v? So that's 3 squared, that's 9, plus 16, that's 25. So the magnitude would be 5, but v dot v, remember, is the magnitude of v squared. So this is 25. So u dot v, 16 over 25 times the vector v. So this is 16 over 25, scaling the vector v, so times the vector 3, 4. And that is my projection. So that's what, 48. Let's see, let's actually compute it. So this is 48 over 25, almost 2. And then we have, 64 over 25. We can calculate these. Let's actually get some numbers so that we can verify in our drawing if this is right. 48 over 25 is 1.92. And 64 over 25, we'll see how accurate my drawing is here, is 2.56. So 1.92, 2.56, again, this is the green vector here, this guy. So yeah, that looks like about 1.92. It's very close to 2 in the x direction and 2.56. My drawing is not totally perfect. Here it looks closer to 2 when really it should be sort of here in the middle. So I've just not drawn this completely to scale. Something is gone sort of wrong in my drawing, just a little bit, but regardless, it's in the right ballpark, and this is what it is exactly. So if I wanted to go back and redraw this with exactly what the projection is, that would be a little bit better, and I would get it. And everything would be orthogonal in that direction, everything exactly in its place. So let's see, and then what's the scalar projection of u onto v? Well, that's just the magnitude of the projection. So we could, one way to do this is to compute the magnitude of the projection, the orthogonal projection. The other way is to use the formula from before. It's u dot v over magnitude v. I already know magnitude v is 5, and I know u dot v is 16, and so this scalar projection then, scalar projection of u onto v, again, this tells me how much of u goes along v, is, what did I say, 16 over 5. So what's that? That's 3 1/5, that's 3.2. And let's make sure we did this right. We also know that the magnitude of the projection should be this scalar quantity over here. So what's the magnitude of my projection of v onto u? I'm going to use my decimal form here. That's square root of 1.92 squared plus 2.56 squared. Let's calculate those. 1.92 squared plus 2.56 squared. Take the square root of that. And amazingly, even though these are sort of, kind of nasty decimals, we get 3.2, which is exactly the scalar projection. So we've done both of these steps right. Excellent. We're done. So that's just a bit of how you can actually compute these projections. In the next video, we're gonna be given an application type problem, and we'll be able to use our knowledge of dot products, these scalar and orthogonal projections, to solve the problem. I'll see you there.